Welcome to a calming journey through the world of nuclear fusion. Beneath the night sky, a quiet expanse stretches in every direction. The stars above shimmer gently, each one a distant sun burning with a silent, ancient fire. But what fuels that fire? What secret warmth allows the stars to shine for billions of years without burning out, without faltering? The answer lies in a process so powerful, so delicate that it shapes the universe itself. That process is called nuclear fusion. Fusion is the engine of the cosmos. It's how the universe builds itself, one atom at a time. It's the reason our sun shines and why our planet is warm enough for oceans, forests, and life. At its heart, fusion is simple. Two light atomic nuclei, often hydrogen, are pushed close together, so close that they overcome their natural repulsion and join into one. In that moment, a small amount of mass disappears. Not lost, but transformed into energy. Einstein's quiet formula, E equals mc squared, tells us exactly how. In stars, this happens every second, countless atoms fusing, releasing immense energy. And yet, from our perspective, the stars seem peaceful, still, serene. On Earth, we've long admired this process from afar. And slowly, carefully, we've begun to ask a simple question. Could we do this too? Could we recreate the power of the stars right here on our own planet? Could we use fusion not to destroy, as in the early years of nuclear research, but to build a cleaner, brighter future? The answer is not straightforward. Fusion is not easy. It requires temperatures hotter than the center of the sun. It asks us to control something nearly uncontrollable. Plasma, a state of matter alive with energy. And yet, despite the challenges, scientists across the world have kept trying. For over 70 years, engineers, physicists, and dreamers have worked in quiet collaboration, trying to unlock fusion's potential. Today, we stand on the edge of something extraordinary. Fusion is no longer just a theory or a dream from science fiction. It is becoming real, bit by bit, step by gentle step. This episode is a journey into that story. Together, we'll explore what fusion is, how it works, and why it matters. We'll start at the very beginning, with the atoms themselves. We'll look closely at how fusion happens in stars and what it takes to recreate that process on Earth. We'll visit great machines like the tokamak and stellarator, strange and beautiful devices designed to tame plasma. We'll gently trace the history of fusion research, from the early days of Cold War competition to the quiet halls of international cooperation today. We'll learn about ITER, a vast fusion experiment in southern France, and the countless people who've poured their efforts into its success. We'll explore what fusion could mean for our future. Clean power, less pollution. Energy without fear. And finally, we'll reflect on what fusion teaches us, about time and about patience, and about the deep connections between science and nature. Because fusion isn't just about energy. It's about harmony. It's about balance. It reminds us that even the most powerful forces in the universe begin with something small. A tiny atom, a quiet reaction, a single step forward. So take a deep breath. Let the noise of the day fade away. And join me as we begin this calm, gentle journey into the heart of a star. What is fusion? At the smallest scale we can imagine, everything is made of atoms. Tiny, invisible structures, each one with a dense center called a nucleus and a cloud of electrons dancing around it. These nuclei are made of even smaller pieces, protons and neutrons. They are the heart of the atom, and they hold nearly all of its mass. Now, imagine two of these nuclei, each one with a positive electric charge. As you bring them close together, they push back, repelling each other like the same ends of two magnets. This repulsion is powerful. It's known as the Coulomb barrier, and under normal conditions, no two nuclei would ever overcome it. But deep inside stars, where the temperatures soar to millions of degrees and the pressure is immense, something extraordinary happens. The particles move so fast and collide so often that occasionally two nuclei get close enough to let a different force take over. This force is called the strong nuclear force. It's much more powerful than the electrical repulsion, but it only works over very short distances. Once the two nuclei are close enough, this force pulls them together and fuses them into one. This is nuclear fusion, a simple name for a very profound process. The most common fusion in stars involves hydrogen dash, the lightest, simplest atom. 4 hydrogen nuclei combine to make one helium nucleus, releasing energy in the process. That energy is what makes a star shine. It radiates outward, lighting up the cosmos, warming planets, and creating the conditions for life. On Earth, we've learned to split atoms, a process called fission. In fission, a heavy nucleus like uranium is broken apart, releasing energy. This is how traditional nuclear power plants work. But fission has risks. It creates radioactive waste, and if things go wrong, the consequences can be serious. Fusion, by contrast, is gentle in its outcomes. Its fuel is often simple dash, like isotopes of hydrogen, deuterium and tritium. These are abundant or can be created safely. And most importantly, fusion doesn't produce long-lived radioactive waste. There's no chain reaction to lose control of, no meltdown risk, no threat to the surrounding world. This makes fusion very appealing, a source of energy that mimics the stars, yet stays firmly grounded in safety. But what does it take to bring fusion to Earth? To understand that, we must go back to nature. The sun has been burning for over 4 billion years. Every second it fuses millions of tons of hydrogen, producing an immense amount of energy. Yet from here, we only feel its warmth gently on our skin. A quiet reminder of the fusion reaction happening above. All stars, not just our sun, are powered by fusion. The bigger the star, the faster it burns through its fuel. But the process is always the same: atoms joining together and releasing light and heat. When massive stars run out of fuel, they collapse and explode in supernova. In those violent moments, even heavier elements are formed, like gold, silver, and uranium. So fusion doesn't just light the stars, it builds the elements of the universe. It created the carbon in your body, the calcium in your bones, the oxygen you breathe. Fusion is more than a reaction. It's a story. A cosmic story of transformation, of creation, of balance. And now, human beings are trying to join that story. Not to control the stars, but to learn from them. To understand their language and speak it gently here on Earth. This is the foundation of all fusion research. The belief that if nature can do it, perhaps we can too. But before we try, we must first understand what fusion asks of us. The next step on our journey is to explore the conditions that make fusion possible. Let's continue to the heart of heat, pressure, and plasma. The conditions for fusion. To make fusion happen, we need to bring atomic nuclei so close together that they merge. But this is not easy. As we saw before, atomic nuclei are positively charged. And like charges repel. This means that to fuse two nuclei, we must overcome a powerful natural resistance, the Coulomb barrier. To do this, we must recreate the conditions found in stars. And stars are not gentle places. Their cores are incredibly hot, millions of degrees, and tightly compressed by gravity. On Earth, we don't have the benefit of that immense stellar gravity. So to make fusion possible, we need to raise the temperature even higher. Much higher. In fact, we need temperatures of at least 100 million degrees Celsius. At that temperature, matter changes. Atoms can no longer hold onto their electrons. Electrons and nuclei separate, forming a free-flowing soup of charged particles. This is called plasma, the fourth state of matter. Not solid, not liquid, not gas, but something entirely different. Plasma glows, it dances and shifts, it reacts to magnetic fields. And it's in this strange, beautiful state that fusion can finally take place. But now we face a challenge. How do we hold something that hot? There's no material on Earth that can touch plasma at those temperatures, not even for a moment. So instead of using walls, we turn to something else. Magnetic fields. Magnetic fields can contain plasma without touching it. They can shape it, twist it, and hold it in place. This is called magnetic confinement, and it's the basis for the most common fusion devices on Earth. The most famous of these devices is called a tokamak. Its name comes from Russian, and it describes a donut-shaped chamber where powerful magnets guide the plasma in a loop. Inside, the plasma spins and swirls, held away from the walls by magnetic force. Another approach is called the stellarator. It also uses magnetic fields, but twists them into more complex shapes, like a helix or a ribbon. These shapes are difficult to build, but they can improve the stability of the plasma. Less wobble, less risk of energy loss. Together, tokamaks and stellarators form the heart of magnetic fusion research. But they are not the only path. There is also a very different method called inertial confinement. Instead of magnetic fields, this method uses powerful lasers or particle beams. A tiny pellet of fusion fuel, often a mix of deuterium and tritium, is hit from all sides at once. The outer layer of the pellet explodes outward, and the core is compressed inward to incredible pressures and temperatures. For a brief moment, just a fraction of a second, fusion takes place. This is a different kind of challenge. It's about speed and precision. In contrast, magnetic confinement is about duration dash, trying to keep the plasma stable for seconds, minutes, or longer. Both approaches are important. Both are being explored around the world. And both are part of the larger journey to achieve sustained controlled fusion on Earth. No matter the method, the conditions must be just right. High temperature to give the particles enough speed. High pressure to bring them close together. And enough time to let the reactions occur. This is sometimes called the fusion triple product of temperature, pressure, and time. It's a kind of recipe, and getting the balance right is what makes fusion so difficult and so beautiful. Even a small improvement in one area can make a big difference. Better magnets, better plasma control, more efficient heating. Each advance brings us closer to creating a tiny controlled star here on Earth. We are still learning, still experimenting, still listening to the language of plasma and trying to understand what it needs. Because once the right conditions are met, something extraordinary happens. Fusion begins. Energy is released. And for a moment, we hold the power of the stars in our hands. In the next part of our journey, we'll look closely at what that fusion reaction looks like, the specific particles involved, and how we might capture their energy to light our world. Let's continue gently to the fusion reaction itself. The fusion reaction, from particles to power. Now that we understand the conditions fusion requires, the intense heat, the high pressure, the delicate balance of plasma, we can begin to look more closely at the reaction itself. What truly happens when two atomic nuclei fuse? What do we get in return? Let's start with a simple reaction, one that's often used in fusion research. It involves two special forms of hydrogen, deuterium and tritium. Deuterium is a hydrogen atom with one proton and one neutron. Tritium has one proton and two neutrons. Both are light, both are positively charged, and both are found, or can be made, here on Earth. When these two nuclei come together, in the right conditions, they fuse. The result is a helium nucleus dash, two protons and two neutrons, and a single high-speed neutron. That flies off with a great deal of energy. This is the deuterium-tritium reaction, often shortened to DT fusion. It's one of the most promising reactions for fusion power because it produces a large amount of energy and occurs at relatively low temperatures, at least by fusion standards. But where does the energy actually come from? It comes from a tiny loss of mass. When deuterium and tritium fuse, the total mass of the helium nucleus and the free neutron is just a little bit less than the mass of the original nuclei. That small difference is converted into energy. Einstein's famous equation, E equals mc squared dash, tells us exactly how much. Even a tiny bit of mass becomes a huge amount of energy, because c, the speed of light, is an enormous number. So in every fusion reaction, a tiny bit of matter disappears and becomes pure energy. This is the energy we hope to capture. To turn into electricity, to light cities, to power homes, to warm water and run machines, without smoke or flame. But there's a catch. Most of the energy from the DT reaction is carried away by the neutron dash, a neutral particle not influenced by magnetic fields. It flies out of the plasma and into the walls of the reactor. There, its energy becomes heat, and that heat can be used to boil water, to turn turbines, to generate electricity. So fusion, like most power systems, still ends up driving a generator. But it does so without combustion, without carbon, and without long-lived waste. The helium that's left behind is not radioactive. It's safe. It simply becomes part of the reactor's exhaust, an inert, harmless gas. The main challenge is that this process must be sustained. You can't just create one reaction. You need billions, trillions happening every second. The plasma must be stable and hot enough for long enough that the reactions continue on their own. This is what physicists call ignition dash, the point where the energy produced by fusion is enough to keep the plasma hot without needing external heating. Achieving ignition is one of the great goals of fusion research. It means the reactor becomes self-sustaining, like a tiny star burning gently within its magnetic cage. But to reach that point, we must also address the material side of the story. The fast-moving neutrons strike the walls of the reactor with incredible force. This puts enormous stress on the materials, causing heat, radiation damage, and potential erosion. Scientists are now developing special alloys and ceramics that can withstand this harsh environment. These materials are critical to any working fusion plant. They must be strong, resilient, and capable of lasting for years. And they must do this while absorbing the neutron energy and passing it along as heat. So a fusion reactor is more than just plasma and magnets. It's a complete system, a delicate, carefully engineered balance of physics and materials, of heat and harmony. And still, it all begins with two tiny nuclei. Two particles in a dance, colliding at high speed and becoming something new. From that moment, light is born. And with it, a future dash, quiet, clean, and full of promise. In our next section, we'll step back in time to see how humanity first tried to tame fusion and the long, steady path that's brought us to the present. Let's gently begin our journey through fusion's history, from the first sparks of understanding to the great machines of today. The early quest for fusion. Our story now shifts from the stars above to the ground beneath our feet, to the quiet halls of laboratories, the clatter of chalk on blackboard, and the steady hum of machines trying to hold the heat of a star. The idea of nuclear fusion did not begin in a reactor. It began in the sky. In the early 20th century, scientists were beginning to understand how stars worked. In 1920, British astronomer Arthur Eddington proposed that the immense energy of stars must come from the fusion of hydrogen into helium. It was a bold idea, and a correct one. By the 1930s, the physicists like Hans Bethe had worked out the details of stellar fusion. They realized that stars weren't burning, in the chemical sense, dash. They were transforming matter into energy through fusion reactions. But the idea of recreating that process on Earth took time. It wasn't until the 1940s and 50s that serious attention was given to controlled fusion. During this period, the world was gripped by the Cold War. Nuclear science had taken a darker turn, fueled by the development of atomic bombs. The hydrogen bomb, first tested in 1952, used fusion, but not in a peaceful way. It released its energy through the uncontrolled fusion of deuterium and tritium, triggered by a fission explosion. Yet even in the shadow of weapons, some scientists began to wonder, could fusion be tamed? Could it be used not for destruction, but to power cities? So began the earliest efforts to create controlled fusion. These projects were often secret, tucked away in military research centers, on both sides of the Iron Curtain. In the United States, projects like Project Sherwood attempted to build early fusion machines. In the Soviet Union, scientists like Andrei Sakharov and Igor Tamm began work on a device that would later be called the tokamak. These early machines had names, like Zeta, Scylla, and Stellarator. They looked strange. Coils, tubes, and chambers designed to hold plasma in magnetic fields. At first, the results were unclear. Some experiments showed brief flashes of fusion, but not enough to sustain a reaction. Some measurements turned out to be mistakes, It was a time of hope, tempered by hard lessons. Fusion would not be easy. In 1958, a shift occurred. At the Geneva Conference on the Peaceful Uses of Atomic Energy, fusion research was declassified. For the first time, scientists from around the world could share their progress. Collaboration began. Ideas were exchanged, mistakes were corrected. And it became clear that fusion was a shared challenge, one that might be solved faster together than apart. In the 1950s, it was the Soviet Union that made a decisive breakthrough. At a time when most nations were exploring different ways to hold plasma, a group of Soviet physicists began to imagine something different. A magnetic bottle, a new shape that might tame the heat of fusion. Two men stood at the heart of this quiet revolution, Andrei Sakharov and Igor Tamm. Together, they designed a machine, unlike any other at the time. They called it the tokamak, short for toroidal chamber with magnetic coils. The tokamak used a donut-shaped chamber with powerful magnets that wrapped around it, guiding plasma in a continuous loop. Inside, an electric current ran through the plasma itself, creating a secondary magnetic field, helping to keep the particles confined. This concept was elegant, stable, and soon surprisingly effective. In the late 1960s, experiments at the Kurchatov Institute in Moscow showed that the tokamak design could achieve plasma temperatures and confinement times far better than any device in the West. But in the atmosphere of the Cold War, these results were met with skepticism. Could they really be true? To answer this question, a British team from the Cullum Laboratory was invited to Moscow in 1969 to take measurements themselves. They confirmed the results. The Soviet tokamak had achieved what no other fusion device had. From that point on, the world embraced the tokamak. It became the foundation of global fusion research. Today's largest fusion experiment, ITER, is built on the same principles first outlined by Sakharov and Tamm. Their invention was not loud, not explosive, but it changed the course of energy research forever. A soft answer to a hard problem, a simple shape hiding immense complexity. And above all, a reminder that even in divided times, science can offer common ground. By the 1970s and 80s, fusion research was expanding. The United States built machines like TFTR at Princeton and D3D in California. Europe launched JET, the Joint European Torus, in the UK. Each machine added to our knowledge. Each experiment brought new insights. Plasma physics advanced. New heating techniques were developed. And slowly, we moved closer to conditions where fusion could be sustained. This period also saw the birth of inertial confinement fusion. In this approach, researchers used lasers and particle beams to compress small pellets of fuel. It was a different strategy. A sudden violent burst of fusion instead of the steady containment of a tokamak. Both approaches were valid. Both held promise. But through it all, progress remained slow. Fusion was never going to be quick. The temperatures required were immense. The materials needed were advanced. The science was subtle and complex. Yet something beautiful emerged in those early decades. A community of researchers spread across continents, working quietly on a shared dream. They understood the stakes. They believed in the promise, an energy source that could last for millions of years, without smoke, without fear. And so, the early quest for fusion laid the foundation for everything to come. In the next subsection, we'll step into the machines themselves, tokamaks, lasers, and stellarators, and see how they try to bring the stars a little closer to Earth. Fusion devices, tokamaks, lasers, and stellarators. If we wish to create fusion on Earth, we need tools that can hold the sun in a bottle. Not literally, but something close. We need machines that can control plasma, hot, energetic, and alive, without ever letting it touch a surface. Over the years, 3 main designs have emerged, each one different, each with its own quiet beauty. The first and most widely studied is the tokamak. Its name comes from Russian meaning toroidal chamber with magnetic coils. Imagine a donut, hollow in the middle. Now imagine that inside this shape, a ring of plasma flows, guided by strong magnetic fields. In a tokamak, these fields are created by large coils that wrap around the chamber. They produce a field that loops the plasma around, keeping it away from the walls. But the tokamak has another trick. A powerful current is passed through the plasma itself, creating a secondary magnetic field that helps keep it stable. This combination dash, external coils and internal current, creates a magnetic cage, a soft prison of force within which the plasma can swirl. Tokamaks are now the most developed fusion devices. They've been built in many countries, from small labs to massive facilities. Machines like JET in the UK, DII in the United States, and K-Star in South Korea have all used the tokamak design. And the largest of all, ITER, now under construction in France, is also a tokamak. It aims to demonstrate that fusion can work at a power plant scale. But tokamaks aren't the only design. Another device takes a different approach, the laser-driven fusion reactor, used in inertial confinement fusion. Here, there is no donut, no swirling plasma, no magnetic field. Instead, there is a small pellet, often no larger than a peppercorn, filled with deuterium and tritium. This pellet is placed at the center of a chamber filled with powerful lasers. When the lasers fire, they strike the pellet from all sides. The outer surface of the pellet explodes outward, and in doing so, compresses the core inward to the point where fusion occurs. It happens in a flash, a tiny burst, a star born for less than a billionth of a second. This method doesn't aim to hold the plasma steady. It simply creates the right conditions. for a brief moment and then releases them. The largest of these laser fusion facilities is the National Ignition Facility, or NIF, in California. In 2022, NIF made headlines by achieving ignition dash, producing more energy from fusion than the energy absorbed by the fuel. It was a quiet, historic step. But laser fusion still faces challenges. The reactions are not yet frequent enough, nor the equipment efficient enough to create power on demand. Still, progress continues, and the promise remains. There is one more design worth knowing, less famous but just as fascinating. It's called the stellarator. At first glance, a stellarator looks like a twisted tokamak, all coils and curves and complexity. But the difference lies deep in the physics, where the tokamak relies on an internal current. To help confine the plasma, the stellarator uses only external magnets. These magnets are shaped in precise, three-dimensional forms, bent like ribbons, curved like waves. They guide the plasma in a stable path, without needing to run current through it. This makes stellarators naturally steady. They can operate continuously, something tokamaks still struggle to achieve. But their construction is far more difficult. The coils must be engineered with exquisite precision. Even the smallest error can disrupt the plasma's path. The most advanced stellarator today is Wendelstein 7X, located in Germany. Its name may be complex, but its purpose is simple: to test whether stellarators can hold hot plasma safely and stably for long periods. The results so far have been promising. Stellarators may play an important role in the long-term future of fusion energy. So we have these three paths: the tokamak with its magnetic embrace, the laser with its sudden compression, and the stellarator with its elegant coils. Each one is an attempt to understand plasma, to speak its language, and offer it a home. Each one is a quiet step toward a future powered not by fire, but by light. In our next subsection, we'll gently explore the challenges that remain, why fusion has taken so long, what we've learned, and how each attempt brings us closer to holding a star on Earth. Why fusion is hard, and what we've learned. Fusion is beautiful, but beauty often hides complexity. And fusion, for all its elegance, has proven to be one of the most difficult challenges in the history of science. To fuse atoms on Earth requires a balance so delicate, so precise, that even the smallest mistake can cause the reaction to fade. The first challenge is plasma control. Plasma is not a solid, not a liquid, not even a gas. It moves like a fluid, but it carries electric and magnetic fields of its own. This means it pushes back against the very magnets, trying to confine it. Even the tiniest irregularity, a ripple, a twist, a bump in the magnetic field, can cause the plasma to drift, cool, or break apart. This is called a plasma instability, and it has been the downfall of many fusion attempts. To control these instabilities, scientists have developed complex systems of feedback, sensors, and precision shaping. They've learned how to gently twist the magnetic field, how to balance pressure and current, how to guide the plasma without touching it. But even when the plasma holds together, another challenge appears: energy loss. The plasma radiates energy in the form of light and particles. This means it cools down over time. And if it cools too much, fusion stops. Scientists must constantly add energy to keep the plasma hot. They use powerful microwaves, particle beams, and magnetic compression. But all of this requires power. So a key question emerges: can we get more energy out of fusion than we put in? This is the heart of the fusion puzzle. Physicists use a term called Q-value dash, the ratio of energy produced by fusion to the energy required to sustain it. A Q-value of 1 means break even. Q greater than 1 means net gain. For decades, fusion experiments hovered below that line. The reaction worked, but not for long enough, or not hot enough to sustain itself. In recent years, that has begun to change. In 2021, experiments at the Joint European Torus produced over 59 megajoules of energy in one 5-second pulse, the highest yet achieved in magnetic fusion. And in 2022, the National Ignition Facility in the US reported a net gain in laser-driven fusion, a Q-value greater than 1. It was a quiet milestone, years in the making. But reaching net gain is not the same as building a power plant. Fusion still needs to work reliably, economically, and on a large scale. We need materials that can survive constant neutron bombardment. We need systems that can extract and convert heat into electricity. We need machines that can run not for seconds, but for months, years, decades. All of this takes time. But time, as fusion reminds us, is part of the process. We've also learned something just as valuable: that fusion is not a race. It's a collaboration. No single nation can solve it alone. Projects like ITER, which brings together 35 countries, have shown how science can cross borders, quietly, patiently, and with shared purpose. We've learned that small experiments matter just as much as large ones. Every test, every failed run, every unexpected result adds to our understanding. We've learned to listen to plasma, to respect its rhythm, its subtle language. And perhaps most importantly, we've learned that fusion is worth waiting for. Because unlike fossil fuels, fusion won't run out. Unlike fission, it doesn't leave behind dangerous waste. And unlike many technologies, it brings us closer to nature, not further from it. The stars have been using fusion for billions of years. They've given us life, light, and time. And now, slowly, carefully, we're learning to do the same. In the next section, we'll turn to the present moment. To the machines that are running today, the teams working across continents, and the quiet progress being made towards a future powered by fusion. ITER and the global fusion effort. In the quiet hills of southern France, a remarkable project is taking shape. Tucked between trees and mountains, the town of Saint-Paul-les-Durance is home to something extraordinary, a machine designed to hold a star. Its name is ITER. It stands for International Thermonuclear Experimental Reactor. But the word ITER in Latin also means the way. And in many ways, ITER is just that, a path toward fusion energy. This is not just another experiment. It is the largest fusion project ever attempted. A tokamak so vast, its central magnet is taller than a house and more powerful than any ever built. The reactor chamber will weigh over 23,000 tons with over 1 million parts, assembled from around the world. ITER is an international collaboration. 35 countries have come together to design, fund, and build it. Members include the European Union, the United States, Russia, China, India, Japan, and South Korea. Together, these nations share knowledge, resources, and a single purpose to prove that fusion can work at a meaningful scale. ITER is not a power plant. It will not supply electricity to the grid. Instead, its goal is to demonstrate something crucial: net energy gain. ITER is designed to produce 10 times more energy than it consumes to heat the plasma. That means for every 50 megawatts of input, it could generate 500 megawatts of fusion power, a milestone never before achieved. To do this, ITER will use a mix of deuterium and tritium fuel, the most promising fusion reaction. Its plasma will reach temperatures of 150 million degrees Celsius, 10 times hotter than the core of the Sun. The magnetic coils, made from advanced superconductors, will create a field strong enough to hold that plasma in place. Every component of ITER is a marvel of engineering. Its central solenoid, a massive vertical magnet, will drive current through the plasma to shape and control it. Its blanket modules lining the inner walls will absorb heat from fusion and manage neutron flow. And its vacuum vessel, made from layered steel, must hold the fusion environment, free from contaminants, leaks, and imperfections. Construction of ITER began in 2010. Piece by piece, components arrived from across the globe. Some were shipped by sea, then carried carefully on custom-built roads through the French countryside. Others were assembled on site in vast halls of quiet precision. Thousands of engineers, scientists, and skilled workers have contributed to its progress. Despite the complexity, the work continues steadily. The goal is to achieve first plasma in the early 2030s, the moment when the machine comes alive. After that, ITER will begin a long series of experiments, testing different heating systems, fuel types, and magnetic configurations. The tritium fuel will be added later, once all systems are ready, for full fusion operation. Though the timeline is long, every step brings new knowledge. ITER is not a race. It is a shared project of patience and precision. Its discoveries will help inform the next generation of fusion plants, machines designed not just to study plasma, but to power cities. Already plans are being made for such reactors. One is called DEMO-, a demonstration power plant that could follow ITER by the 2040s. It would take what ITER proves and apply it in a practical, energy-producing way. All of this has been made possible by cooperation. No single country could build ITER alone. Its complexity, its cost, and its purpose are shared among many. This makes ITER a symbol of something greater. Not just scientific progress, but international understanding. A project not built in haste, but with the quiet conviction that working together, we can do more. As ITER moves forward, it carries with it the hopes of generations of scientists, those who imagined fusion when it was only theory, and those who will make it real. In the next subsection, we'll look more closely at recent breakthroughs, how new tools, ideas, and experiments are helping accelerate the journey toward fusion energy. Recent breakthroughs in fusion research. The journey to fusion has never been a straight path. It twists gently through decades of quiet effort, some steps forward, some sideways, and many moments of slow learning. But in recent years, the pace has begun to shift. Not in a rush, but with a steady confidence. Small breakthroughs have begun to add up. These advances are not always loud, but each one brings fusion closer to being more than a promise. They turn theory into practice. They light the way forward. One of the most notable milestones came from a place we've already visited, the National Ignition Facility, or NIF, in California. In late 2022, NIF achieved something extraordinary. It reached ignition. In a single laser-driven experiment, more energy was released by fusion than was absorbed by the fuel pellet. A Q value greater than 1, a point fusion scientists had sought for more than 60 years. It didn't mean commercial fusion was ready, but it did mean that fusion, in principle, could produce more energy than it consumed. It was a moment of quiet celebration, a sign that fusion is not just a dream, but a real possibility. While NIF focused on inertial confinement, magnetic fusion has also seen steady progress. In 2021, scientists at the Joint European Torus, or JET, achieved a record-breaking energy output of 59 megajoules over 5 seconds. It was the most sustained fusion power ever produced in a tokamak. And perhaps more importantly, it confirmed many of the design choices being made. For ITER, breakthroughs have also come from smaller private efforts. In the United States, a company called Commonwealth Fusion Systems built a powerful new magnet using high-temperature superconducting tape. This magnet reached over 20 Tesla, stronger than any tokamak field to date. This strength could allow for smaller, more efficient reactors, reducing cost and speeding development. It marked a turning point. Superconducting magnets have long been key to fusion, but older materials required extremely cold temperatures and bulky designs. High-temperature superconductors are lighter, more flexible, and can carry more current. These materials may enable the next generation of reactors to be built faster and at smaller scales. At the same time, our tools for understanding plasma have improved dramatically. Modern diagnostics can measure plasma behavior with remarkable precision. We can now track turbulence, magnetic islands, and energy flows in real time. This helps researchers adjust conditions mid-experiment and model results more accurately. Meanwhile, simulations have become far more powerful. Supercomputers can now model the entire behavior of plasma inside a reactor, from particle collisions to wave propagation. This allows scientists to test new ideas before building them, saving time, money, and effort. One recent breakthrough involves the concept of advanced diverters, special components that handle plasma exhaust. Diverters remove heat and particles from the edge of the plasma without disrupting the core. New designs, like the SuperX diverter, spread the heat over a larger area, protecting materials and extending reactor life. These kinds of innovations, small in scale but vital in function, are shaping the reactors of tomorrow. Private companies have also entered the scene. Firms like TAE Technologies, Helion Energy, and First Light Fusion are experimenting with alternative geometries, fuel types, and compression methods. Each has a different vision, but they share a common goal to make fusion practical, affordable, and scalable. Government laboratories, academic institutions, and private enterprises are now working together more than ever before. This blended approach brings energy, diversity, and momentum to a field once dominated by slow timelines. And still, through all these changes, fusion remains steady in its principles. The goal has not shifted. It is still about bringing two small atoms together and capturing the light they release. It's just that now, we have more tools, more minds, and more ways to try. In the next subsection, we'll look at the people behind fusion, how their efforts stretch across borders and generations, and how this shared endeavor continues quietly, patiently, toward a future lit by stars. The fusion community, collaboration and continuity. Behind every fusion machine, every coil, every line of code, there are people. People who have dedicated their lives to the gentle art of understanding plasma. Some work in vast facilities, others at quiet desks, poring over equations or adjusting control systems late into the night. Fusion is not the work of a single genius or a single decade. It is the work of a community, one that stretches across continents and generations. The path to fusion is long. Many of the researchers who began this journey in the 1950s and 60s are no longer here to see how far it has come. But they trained students, and those students trained others. And now, a new generation of physicists, engineers, and technicians has picked up the thread. There is something deeply human in this passing of knowledge. Fusion teaches patience, not just scientific, but generational. It teaches us that progress may not come quickly, but it comes steadily when shared. Collaboration has always been at the heart of fusion. From the earliest days, scientists from different nations have gathered at conferences, shared data, and compared notes. In the 1950s, fusion was still bound by secrecy. But by the 1960s, trust began to grow. By the 1980s, it had become clear that fusion could not be solved alone. Today, that spirit of openness continues. The ITER project, perhaps the most visible example, brings together engineers from Europe, Asia, and the Americas. Each nation contributes different parts. Some build magnets, others build cooling systems, or power electronics, or cryogenic lines. It is a global puzzle, assembled piece by piece with quiet precision. But collaboration happens in smaller ways too. Students travel between labs. Postdoctoral researchers share software. Plasma physicists debate results in long video calls that stretch across time zones. And every so often, a breakthrough emerges, not from one lab, but from many minds, thinking together. There is also great diversity in the kinds of people who now work in fusion. Women and men from all backgrounds, physics, engineering, computer science, materials dash, each bring a different lens to the same problem. Some model turbulence, some test new alloys, some write control code that responds to plasma in real time. Fusion is more than theory. It is hands-on. It is practical. It is deeply collaborative. And because the goal is so long-term, there is often less competition and more trust. Labs share designs. Teams publish openly. Retired researchers return to mentor the next wave. It is a culture of continuity. One where progress comes not from rivalry, but from quiet persistence. This community has also faced its share of disappointments. Fusion has often been promised in 30 years, and that promise has been repeated for decades. But most within the field understand this is not failure, it is the nature of the problem. Fusion is hard because it is worth doing right. There are no shortcuts, no easy wins, only careful steps and the quiet confidence that each one matters. And so, the fusion community moves forward. One experiment at a time, one paper at a time, one shared idea at a time. It is science at its most generous, slow, open, hopeful. And as the community grows, so too does the understanding that fusion is not just a scientific goal, but a shared human endeavor. A symbol of what we can do when we build not in competition, but in common purpose. In our next section, we'll gently explore the future that fusion could offer. A world of clean, quiet energy, and what it might mean for our lives, our planet, and generations to come. a new kind of energy. Energy is all around us. In the light we switch on at night, the warmth in our homes, and the quiet current that powers the devices in our hands. But for over a century, much of this energy has come from the same place: burning fossil fuels, coal, oil, and gas. They have powered great advances, but also brought pollution, climate change, and a deep dependence on finite resources. In response, the world has begun to shift. Renewables like wind and solar are growing. Nuclear fission continues in some countries. But fusion offers something different. Not just a replacement, but a transformation. It promises an energy source that is clean, producing no greenhouse gases, safe, with no risk of meltdown or runaway reactions, abundant, using fuels we can find or create with ease. Let's begin with the environment. Fossil fuels release carbon dioxide, the main driver of global warming. They also produce air pollutants that harm human health. Fusion does neither. Its only byproduct is helium, a harmless, inert gas. And it requires no combustion, no chimney, no smoke. Fusion also avoids the long-lived radioactive waste created by fission reactors. While fusion does produce some neutron-activated materials, they are short-lived and far easier to manage. And there is no chain reaction to worry about. If something goes wrong, the reaction simply stops. No meltdown, no mass evacuation. This makes fusion inherently safe. It doesn't require pressurized water or explosive fuels. It can be designed with simplicity and robustness in mind. Then there is the matter of fuel. Fusion uses isotopes of hydrogen dash, primarily deuterium and tritium. Deuterium is abundant. It can be extracted from water. Tritium is rarer, but it can be bred from lithium, a metal found in the Earth's crust, and even in seawater. This means that, in theory, fusion could supply energy for millions of years using fuel that is widely available. No drilling, no pipelines, no geopolitical conflict over oil and gas. Fusion offers energy independence, both for nations and for the world as a whole. And it does all of this while providing the kind of reliable power that modern societies need. Unlike wind and solar, fusion is not tied to weather or sunlight. It can run day and night, summer and winter, without storage or backup. This makes it a strong partner to renewables. While wind and solar provide variable energy, fusion could provide the steady baseload. Together, they could form a resilient, balanced system with low carbon and high reliability. Fusion also has a relatively small land footprint. A single fusion plant could generate as much power as hundreds of wind turbines or acres of solar panels. This would be especially helpful in densely populated regions or places with limited space. Of course, fusion isn't here yet. But as we've seen, the science is advancing. And when fusion arrives, its benefits will be far-reaching. It will help us reduce emissions, limit climate change, and provide stable energy in a changing world. It will offer a cleaner path for developing nations to grow without increasing pollution. It will support the transition away from fossil fuels, not by replacing renewables, but by complementing them. And it will do so without the waste, fear, or fragility that has limited nuclear fission. This is why fusion matters. Not because it's perfect, no technology is, but because it offers something rare, a new foundation for energy. One that is calm, clean, and quietly powerful. In the next subsection, we'll imagine how fusion might be used in homes, in cities, in distant places, and perhaps even beyond Earth itself. How fusion could change our world. Imagine a future where the lights never flicker, the air stays clean, and power flows gently from reactors that hum as quietly as a breeze. This is the promise of fusion, not just as a technology, but as a new rhythm for how we live, how we build, and how we move. In this future, fusion plants might sit near cities, providing steady electricity, day and night. They would not require vast fuel deliveries or produce streams of carbon dioxide. Their fuel could be drawn from the ocean, from lithium, from simple elements already in our grasp. With fusion, homes could stay warm in winter, cool in summer, and lit at night, without polluting the skies. Hospitals, schools, and factories could run without interruption, no matter the weather. Cities might even shrink their environmental footprints, free from the need to burn fuels or rely on coal or gas. But fusion could go beyond just electricity. It could also provide industrial heat, the high temperatures needed to make steel, glass, and cement. Today, these processes rely heavily on fossil fuels. Fusion could replace that with a cleaner, more stable source of thermal energy. Fusion might also help with one of the world's great needs, fresh water. Desalination, turning seawater into drinking water, requires energy. With abundant fusion power, it could become widely available, especially in dry regions, facing drought and population growth. And then there is transport. While electric cars may rely on batteries, other forms of transport, like ships, trains, or planes, need dense, continuous energy. Fusion could power charging stations, hydrogen production, or even be used in hybrid engines for future long-distance travel. There is even talk of space exploration. Fusion rockets, still theoretical, could offer the thrust and efficiency needed to reach other planets. Unlike chemical rockets, fusion propulsion could operate longer and carry heavier payloads, making space more reachable. But even here on Earth, fusion's potential is profound. It could support rural electrification, bring power to remote regions, and reduce dependence on fragile or polluting energy systems. Fusion power plants could be designed large, to serve entire regions, or modular and small, to provide power to a single town or island. They would likely be connected to the grid, but could also work in isolated systems, where needed. In places where sunlight is rare, or where winds are gentle, fusion could quietly fill the gap. It won't replace all energy sources. Wind, solar, hydro, and geothermal will still have important roles. But fusion could form the steady foundation, the low-emission base, on which a flexible modern energy system is built. This shift could also change how we think about energy itself. Instead of scarcity and competition, fusion offers a model of abundance. Instead of extraction and combustion, it offers harmony with nature's own methods. We wouldn't need to dig deep into the earth, or build massive dams, or cover vast land with panels. Just a few light atoms fused gently, releasing warmth. There are, of course, questions still to answer. How will fusion power be integrated into the grid? Will fuel cycles, especially tritium, be managed safely and reliably? How will new materials and components be maintained over years and decades of operation? These are not trivial challenges, but neither are they insurmountable. Each one is being explored by engineers and scientists around the world. And each solution brings fusion closer to becoming part of daily life. A life in which energy flows without fear, without smoke, and without end. In our next section, we'll reflect quietly on what this journey means, not just for science, but for our sense of time, patience, and purpose. The long road to fusion. Some journeys are swift. They follow straight lines, gather speed, and reach their end in a blink. But fusion is not that kind of journey. It has moved slowly, step by careful step, over decades. And though the path has been long, there is something deeply meaningful about that pace. Because fusion is not just a technical puzzle. It's a quiet lesson in patience. From the moment scientists first glimpsed its possibility, they knew it would not be easy. It required heat beyond imagination, materials not yet invented, and theories that had barely been born. Each breakthrough came slowly. A better magnet here, a new diagnostic there. And every advance rested on the work that came before. Some researchers spent their entire careers working on problems they knew they might not live to see solved. And still, they worked. Because fusion is a promise that belongs not just to the present, but to the future. This is rare in our world. Many technologies are designed for speed, to be built, used, and replaced. But fusion asks us to slow down, to think in decades, not months. To understand that some of the most powerful things take time to grow. Like a tree, or a relationship, or a star. Fusion also reminds us that science is not always spectacular. sometimes it's quiet. It happens in long meetings, careful notes, and small corrections. In cleaning instruments, retesting code, and staying curious, even when things don't work. There is a kind of humility in this work. Fusion doesn't bend easily to our will. It asks us to listen, to observe, and to earn its trust through understanding. For many in the field, this has created a deep sense of respect, not just for the science, but for the process. They've learned that progress is not always linear. Sometimes we take one step forward and 2 steps back. Sometimes a result takes years to appear, and when it does, it quietly changes everything. This kind of progress is fragile, but it is also strong, because it is built on trust. Trust in the method, trust in the data, and trust in each other. And in that trust, there is hope. Hope that with time and care and collective effort, we will reach the goal. Fusion, then, is more than a power source. It's a reflection of our better qualities, our patience, our cooperation, and our willingness to invest in a future we may not yet see. And that, in itself, is something rare and beautiful. As we near the end of our journey, let us take one more step to imagine the world that fusion might create. A world lit gently, not by fire, but by light drawn from the heart of the stars. A future lit by stars. Imagine a quiet morning. The sky is pale, the air is clean, and the hum of distant power is almost inaudible. There are no smokestacks, no burning, no scars on the landscape. Yet the city wakes, warm and bright, drawn gently into motion by an unseen light. This is the future that fusion promises. A future where energy is no longer a source of fear or pollution or division, but something quiet, steady, and shared. Because fusion is not just power, it is harmony. It takes the smallest pieces of matter and turns them into something greater. It mirrors the stars, calm giants in the sky, burning not to destroy, but to create. A world lit by fusion would be different. We would no longer fear the limits of fossil fuel reserves. We would no longer wonder if our children would inherit a planet choked by carbon. Instead, we might learn to live with more balance, more care, more awareness of the deep connection between our needs and the universe around us. Energy would flow like sunlight, soft, consistent, and sustaining. We would still build, still grow, still dream dash, but without the toll on air and water that energy once demanded. Fusion could support all life's comforts without asking nature to pay the price. And in that gentle light, we might also change. We might think more about the long term, about the kind of future we want to build, not just next year, but next century. Fusion asks us to be caretakers, not just of the technology, but of time itself. To honor those who came before us, who laid the foundations. To teach those who come after us so they can build further. To move slowly when needed and quickly when the moment calls. Because fusion is not a finish line. It's a beginning. The start of a new relationship between humanity and the energy that shapes us. It is the light of stars held carefully in human hands. So as we close this journey, let us take a moment to sit with the quiet beauty of that idea. That deep in the universe, far beyond our reach, stars have burned for billions of years, not for us, but because that is what they do. And now, after all this time, we have learned enough to follow their example. To bring a little piece of that cosmic fire down to earth. Not in flame, but in light. Not in violence, but in understanding. To light our cities, to warm our homes, to power our future, gently, safely, and together. This is the promise of fusion. And slowly, quietly, we are learning how to keep it.